Hi, welcome to my channel, JaberTime. I'm gonna go over triple integrals in cylindrical coordinates. The two graphs that you could see on the screen now, they explain the concepts of cylindrical coordinates. This is a sample of the integration part of the region E, and this triangle shows that you could refer to a point as x and y or r and theta. In cylinders we go straight up, so it's going to be r, theta, and z. Let me move on and show you more details and some examples. Triple integrals in cylindrical coordinates. You could see I have different colors. The x and y are in blue. To switch from x and y to r and theta, the connections are right there. Y equals r sine theta from a right triangle, and x will be r cosine theta, which is the adjacent side. R will be the square root of x squared plus y squared, and theta will be tan inverse y over x. Same point, x, y, r, theta. Now to convert from cylindrical to rectangular, in rectangular we need x, y, and z. To get x you need r cosine theta. To get y you need r sine theta. To get z, it's the same z. Going the other way around, to convert from rectangular to cylindrical, you need r theta and z. As you could see, z is the same. R will be the square root. Theta will be coming from tan inverse y over x. Here's two practical examples about cylindrical coordinates and graphing at least one of them. Plot the point with cylindrical coordinates 2 pi over 3, and 1. First, before I move on, since we have 2 pi over 3, which leaves us with a reference angle of 60 degrees in the second quadrant, that's right there. That's 2 pi over 3, so what's left is 1/3 pi. It's good to know ahead what is the adjacent, what is the opposite, and what's the hypotenuse if it's a unit circle. If you scale it up times 2 times 2 times 2, that's another way to look at this right triangle. Now, as I said, we have the cylindrical, and it says find the rectangular, which means we need x and y and z. X is r cosine theta, 2 times cosine 2 pi over 3. Cosine 2 pi over 3, which means we are in the second quadrant, and the cosine is -half. Simplify, you get -1. Y will be 2 sine 2 pi over 3, and sine is rad 3 over 2. Times 2 will be just rad 3. Z is the same thing as 1, which is given to me right there. Here's the graph. You're gonna go out with a radius or length of 2. That's a length of 2 from the origin. You're gonna go to the second quadrant, pass the positive y-axis with the angle 2 pi over 3. As you can see, we passed it, and we're gonna go up 1 unit. So we're not in the first octant anymore. We're to the left of the first octant, going counterclockwise. That should do it. That's the graph in cylindrical coordinates. So it's how far you move out as counterclockwise, how far you go away from the origin, and you just go straight up. That's why z is the same as z that we know in 3 dimension. Find cylindrical coordinates of the point with rectangular coordinates 3, -3, -7. Those are x, y, z. Alright? To find r, this is the main formula. You take the square root, plug in 3 and -3, 3 and -3, do the math, and I have 3 square root of 2. If you notice here, I'm trying to save you a lot of time and make the video not more than 30 minutes to the best that I can. That's why I have the notes and I have break it down instead of me going over it with the stylus. So hopefully you appreciate that I'm writing this down ahead of time. I'm going over it a little bit fast, but the concept is what is important. The steps of calculations, you could come back to it and see it again. Here's tan theta, y over x, negative 3 over 3, y over x. Because tan is negative 1, we have 7 pi over 4. Tan is negative. Tan could be negative in the second quadrant or the fourth quadrant, but we're looking at tan inverse. And we have x and y. So x is positive and y is negative. So we are in the fourth quadrant. And that's negative 45 degree plus 360n, or 7 pi over 4 plus 2n pi. Okay? Now, z equals negative 7, which is the same as what is in rectangular. Therefore, one set of cylindrical coordinates is the x, the r, theta, and z. R, theta, and z. R, theta, and z. 7 pi over 4, 3 rad 2, and negative 7. Another one will be 3 rad 2, negative 7, negative pi over 4, as like negative 45, and negative 7. As with polar coordinates, there are infinitely many choices. So something different about rectangular coordinates. Describe the surface whose equation in cylindrical coordinates is z equals r. This is something that you want to keep in mind. Z equals r. A lot of ways you could describe it, but this is what I have for you. Since z equals r, and z is like you go straight up, so z value, kind of like we refer to it as the height. Theta can vary because theta is not mentioned. So you could go around 360 degrees and you're referring to z as the length of r, or the magnitude of r. Any horizontal trace in the plane with z equals r or k, where k is positive, is a circle of radius k. Think about it. If you have r equals 5 and you're saying to me that I'm not on the xy plane because my z is 5 also, that circle with radius of 5 is not on the xy plane. It's up level to the height of 5 units because you said z equals 5 also. So when z equals 4, it's a smaller circle and it's lowered down 1 unit. When z equals 3, it's a smaller circle, you know, and so on and so on. So you do have a cone. These traces suggest that the surface is a cone. By converting the equation into rectangular coordinates, we could do it differently. We could talk about it in a different concept instead of just like meanings, what we described right here. Z equals r, z square equals r square, but r square is x square plus y square. Is a circle cone whose axis is the z-axis. Alright? If you look at it, z square equals x square plus y square. Same thing for z is like same thing for r in this case, which is a 45 degree also. And it goes both direction unless if you want r to be positive. Evaluating triple integrals with cylindrical coordinates. X, Y, Z in rectangular. And we have Z between Z1 and Z2, a function of XY, a function of XY. Now, type 1. Projection on the XY plane, because they say like now down your XY belongs to D, which is the projection. So we are projecting down on the XY plane, and that's why they call it type 1. Once you project down, think about a cylinder, we're gonna think about circles, and that is polar language. Whenever you see circles, think about polar. You reduce your work a lot and you finish faster. So the region D, the projection, is r theta, where theta ranges from alpha to beta, and r changes from a function of theta 1 to another function of theta. So the triple integration over the region E in 3 dimension of fxyz dv will become of this format. You change x to r cosine theta, you change y to r sine theta, and z you keep it as z, and now we have r dz dr d theta. Alright, just keep this in mind. The green one refers to z, the blue one refers to r, and theta refers to alpha and beta, or d theta. Now to support this right here, looking at this graph, imagine if you have a cylinder filled as a volume with liquid or whatever, and you want to slice it. You're not going to slice it like small boxes, like in triple integration with rectangular dimension. So if you want to slice it like, with a circle motion right here, another circle right here, bigger one, and you want to slice it this way, kind of like going with the radius, we're going to have a slice like this one. This is a sample. Well, to find the volume of this sample, that's going to be dv, or delta v. It has 3 dimensions. This dr is part of the game, this dz is part of the game, and this here going around, this is part of the circumference, which is called arc length, and this arc length is r d theta. I showed you this like in about 2-3 videos ago, and I'll put the description or the video link at the end if you need more help understanding why this is r d theta. I covered it in depth, how to show the length of, I remember 2 things, the area of a sector and the arc length. So anyway, so this is part of a circle circumference. We call it arc length, r d theta. So you have r d theta dr dz will cover the 3 dimensions, and this is something you want to keep in mind, which is called dv. So if you go back right here, this is my dv, r dr d theta dz. Alright, here's an example. A solid E lies within the cylinder x squared plus y squared equals 1 below the plane flat horizontal, z equals 4 above the paraboloid z equals 1 minus x squared minus y squared. That cylinder is so clear. If you don't see 3 dimension, it's a circle with radius 1 in the xy plane. Z equals 4 is a horizontal plane leveled at z equals 4. Z equals 1 minus x squared minus y squared. It's like a parabola in 3 dimension, upside down, opens downward, and shifted up 1 unit, if you want to think about it this way. Here's the graph to support. This level is z equals 4. This is the cylinder. Because we are in 3D, we're not going to call this a circle. X squared plus y squared equals 1. Goes on the x-axis up to 1. Same thing for the other sides. And this is a parabola in 3 dimension. You're gonna be shifted up to 1, as you can see on the z value. So what we have here, the region E is within the cylinder, below z equals 4, above this right here. Alright, so this region right there. Okay, the density at any point is proportional to its distance from the axis of the cylinder. This is an application to show you that the triple integration is not a volume. It's a volume if what's inside the function f of x, y, z is 1 only. Keep that in mind. So the density is proportional to the distance from the axis of the cylinder. Find the mass of E. The density is our function. F of xyz equals k times, this is square root of x squared plus y squared, which is r. It says proportional to the distance from the axis. Kind of like you're going out from the axis, which is like radius, and radius changes from 0 if you want to fill it, not just trace the circle, from 0 to 1. So we're going to call it r. And k would be the proportionality constant. Now, looking at the cylinder, we're not going to keep it x's and y's, guys, as you could see. We're looking at the cylinder. The cylinder is x squared plus y squared equals 1. That is differently r squared equals 1 or r equals 1. Looking at this in red, which is the paraboloid z equals 1 minus x squared minus y squared, that could be written differently as z equals 1 minus r squared. So the region E right here within the cylinder above the paraboloid is being called r theta z, where r varies from 0 to 1, theta varies all the way around from 0 to 2 pi, and z from this surface from 1 minus r squared up to this ceiling, which is 4. So if you are inside here, what's below you is this, and what's above you is this right here, z equals 4. Something to keep in mind, z1 and z2. The mass of E, m, will be the triple integration of the density function that we have here, dv. Now, transferring to polar and cylindrical coordinates, we have kr for the density function. We have r dz dr d theta that we agreed on. z1 in green goes with z from 1 minus r squared to 4, from 1 minus r squared to 4, and r goes from 0 to 1, theta goes from 0 to 2 pi. All this work is to get this formula. I keep saying that. Without building this right here, it's hard to start or finish or integrate. You need the right components, the right limits, the right order to finish. And this is the major part or most of the work. After that, it's calculations, integration, steps, filling in whatever is needed, and move on. Let's take a look. Integrate this with respect to z. I have no z inside. This is k times r, which is kr squared, will be multiplied by z. Then plug in z equals 4 and 1 minus r squared. Once you do that, you are now integrating with respect to r. From 0 to 1. It has r's inside, just regular math. Integrate, or you could separate. There is nothing here talks about theta, not even the limits. So you could take this to the side as another factor. We took the k out all the way out. This is a simple integration. This is a simple integration, which is known as 2 pi. And you do the math. And the answer is 12 pi k over 5. That should do it for this problem. Let's move on. Evaluate the triple integral. See, we don't know what is going on, so they're not calling it volume. Now, if somebody gives you this, you need to understand the limits. They're not describing the graph. They're not telling me below and above and under and so on. So what's going on? Let's take a look. First of all, my function is x squared plus y squared. All right. Look at my limits. This sounds like r. This sounds like z equals. Okay, z. Have you seen this before? Look at these ones. Those are part of semicircles. And those are constants. They're supposed to be constants at the end. They're supposed to be constants. Here's the graph. Our main function is x squared plus y squared. Our lower part is z equals square root of x squared plus y squared, or z equals r. Z equals r is a cone. You have to keep this in mind from now on. Z equals r is a cone. And if it doesn't have anything in it, like 2r or so on, it's a 45 degree. The top z is 2. So we have a flat horizontal surface, z equals 2. Now, if you take your time and do the math, this goes up to 2. So we have 2 here marked on the z-axis. And if you take this part and drop it down, you're going to have a circle with radius of 2. Why? Because z equals r. This z is 2, this r is 2. So we have 2 down right here on the positive y and the positive x-axis. So our region inside E is xyz, still in rectangular, where we have z varies from those limits. I'm just, instead of reading them, I'll point to them up here. Those are my limits, but they're not in color. It's the same thing, where z varies from 2, and y varies from 2, and x varies from 2. That's what this is saying. In cylindrical coordinates, which is going to make our life easier, it's r, theta, and z. Whenever you see a circle, it's a polar language, r, theta. And because we are dealing with cones or cylinders, that's called cylindrical. We are in 3 dimension, r, theta, and z. Now, the same thing is described as r goes from 0 to 2, from 0 to 2, from 0 all the way up to 2 to cover the whole region inside. Theta goes all the way around 2 pi, and z goes from r to 2. So if you make an arrow right here, that's from r to 2. And that is called type 1 integration. So let's go back to the problem. The problem says evaluate the following. This is r squared. dv is r dz dr d theta. Now we have r cubed. With those limits that we agreed on, look at this. After that, I could go fast because it's just integration one after the other, knowing that we have to integrate inside first with respect to z, then with respect to r, then with respect to theta, and move on. Or do whatever you want as long as you are doing it correctly. There is no theta here, so we could pull it outside if you want. So we have r cubed. That's going to give you, let's see. With respect to z, r cubed is not going to change because we're going to treat r and theta as constants. So I do have r cubed times z, plug in 2, plug in r with the minus sign, that's 2 minus r. That is replacing this whole package right here. Integrating with respect to z and plugging in the limits to an r. Once you do that, now you are with respect to r from 0 to 2 integrating. 2 pi is done, out of my way. This right here with respect to r is just like regular math. So let's move on and not read it. I'll leave it up to you. I think that should be fine. The main part is, do you get this part and how to translate what they are saying to a cylindrical coordinates with the right limits. After this, I have 16 over 5 pi, and I think that should do it. As planned, less than 30 minutes, and that was my goal, and hopefully that was not too fast. Thank you. I'll see you next time. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.